All right. So what we're going over today is conservation of mechanical energy, which will be entirely review from Science 10. Okay, nothing has changed about the law of conservation of energy since last year, thankfully, because it's kind of one of those fundamental things we depend on for how the universe works. Okay. Also, there's not going to be any really more difficult questions than you would have done in Science 10 either. Okay, this will be very similar to the roller coaster questions you would have done last year, except we'll just do different situations than always a roller coaster like it was in Science 10. Okay, so we need to understand a couple things. First off, that energy cannot be created or destroyed. Okay, you can transfer it to other things, you can change it into different forms, but you cannot create it, you cannot destroy it. It will always be there. It just may not be in a form that is useful anymore. Okay, understand that energy can be converted from one form to another, and then obviously use this concept to solve problems for certain variables. Right, that's what we'll be looking at today. All right, so as part of mechanical energy, we have the two kinds of energy we went over yesterday and the day before. Potential energy and kinetic energy are the two types. They fit into mechanical. Okay, so that's what we have there. We have been working on this idea here, that work is the change in mechanical energy. That is final kinetic plus final potential minus initial kinetic plus initial potential. If energy is conserved, then what is this number? If I'm in a situation where all the energy gets conserved, what's the difference between the final and the initial energies? Zero, right? So there would be no work done. Okay, when there is no work done, then we can say the initial mechanical energy equals the final mechanical energy. Okay, because there's no difference between the two, right? And then what we would have would be our EP initial plus our EK initial equals our EP final plus our EK final, okay? And we know what the formulas are for each of those energy types. We just expand that out further, okay, until we can start solving for something we don't know. Okay, so in other words, the final mechanical energy in an energy conserved situation is equal to the initial. Okay, consequently, the total mechanical energy remains constant all the way from point A to point B along the path the system or object is traveling. Okay, so if we had this example here with this like wild roller coaster with these giant oval loops on it, okay, this up here, the energy would be mostly what? Mostly potential. Maybe there's a little bit of kinetic or something like that. As it moves down, the potential will decrease, decrease, decrease until when we're down here, the potential would be theoretically zero because we can't fall any further. This is where we would be moving the fastest, right? All of our energy is now kinetic. When we go back up into the loop, we slow down because now we're turning that kinetic energy back into potential. Okay, when we get to the top of the loop, we have a little bit of both. If we didn't, you'd stop at the top of the loop, which might be exciting for the first 2 minutes or so, but after that, it wouldn't be fun anymore. Okay, and then you'd come back down the loop, accelerating as you came down. Okay, obviously you'd be turning that potential back into kinetic, and so on as you go over all the little bumps. Now, obviously in the real world, energy is not conserved, which is why the first hill is the highest point on the ride. No other point on the ride can be that high unless work is done on the roller coaster at some point during the ride to add energy to get back up there. Otherwise, you'll never have enough energy to get back up to that height. All right, everybody follow me on that? Okay. Now, as you all know, I'm a geek. If you haven't realized that, it's true. First step in overcoming a problem is admitting you have one. I don't have a problem with being a geek, and I'll fully admit that. Okay. I'm so much of a geek that when my track team went to provincials in Edmonton, I saw this thing. And I got really excited. In fact, I brought the whole team over because I'm a geek. Okay. And they're like, Coderre, it's a ramp. I know, but you have to see, you have to watch it. Okay. What they would do, this thing was actually designed, I found out later, okay, in the engineering faculty at the U of A. It's designed so that when you put a shot put up here, at the top of the ramp, it'll roll down the ramp, converting its potential energy into kinetic, and the amount of friction there is along the flat part of this rail makes it come to a stop right at the end. Unlike the bowling alley, where if you accidentally get your fingers in between the bowling balls as they're rolling back, you'll get them crushed. Okay, this one, it actually rolls to a stop. So they calculated how much work would be done against friction over this distance and just made sure they made the ramp high enough that it would have that much potential energy to start with. Okay, no one realizes that when they look at it. They just see a ball rolling down a ramp. Okay, you guys have to get to that point where when you see something like this, you're like, oh, holy crap, that is so cool. But you don't have to admit it to anybody. Okay, just say it in your head. Not like me, who brings this entire track team over to show them how cool it is and then feels a little embarrassed afterwards. Okay, especially since all these onlookers were like, God, that guy's such a geek. And it's true, but I'm fine with that. Okay, so it's a good practical application of this whole work energy theorem idea, okay, put into practical use. Okay. Other practical uses for the law of conservation of energy and the work energy theorem is the design of, obviously, amusement park rides, but also the design of a lot of winter sports facilities. And if you guys recall, back when we had the Winter Olympics in Vancouver, well, you guys might not remember that because you were quite young then, but on the opening day, or the day before the opening day, there was a guy, a skeleton guy, who was killed on the track on the very first day. Okay? And the reason that happened was the track ended up being more slippery than they had anticipated. And as a result, when he got to the first corner, he was going faster than they thought anyone would go when they got there. And he went off the track and he was killed. Because when you ride skeleton, that's the one where you ride on the luge head first, right? As if luge wasn't crazy enough. Okay? People said, that's not exciting. I want to go head first instead. Okay? So he went up, but he went off the track and he was killed. So what they ended up having to do was they had to change the track. And obviously they couldn't really restructure the track in one day. So all they did was start people lower down on the track. How did that fix the problem? They had less potential energy. Okay? There was no way then that they would have enough kinetic energy at that first corner to fly out of it anymore. Okay? Kind of a simple solution, okay? But it's too bad they didn't think of it before that poor guy went off the track. Okay? But this is a practical application of design. You need to know about how much energy something's going to have at any point on the track. Otherwise, you're going to be in trouble. Water slides, same thing. Okay? You don't design a water slide properly, and someone will fly out of it on a corner. That's why most of the time on corners of a water slide, they go up higher, right? The corner is built higher than the straight sections because they don't want people to fly out on those corners. Okay, so what we need to understand about the law of conservation of energy is obviously that the total mechanical energy of the object remains the same all the way along the course. Okay, what does change is how much of that is potential and how much of that is kinetic. So obviously we start out with 600,000 joules of mechanical energy, all of it being potential. And then as we go down the track, we convert some of that potential into kinetic, but our total always adds up to 600,000 joules. Okay, in this case, guys, in the case of conservation of energy, gravity is the force that does the work. If there are any other forces, energy will not be conserved. Okay? Only gravity can be doing the work. And so obviously in the real world, that never happens. Okay? Even if you were to jump out of a plane, okay, you still have air resistance, okay, that would be acting on you there. So it wouldn't be a perfect law of conservation of energy question, okay, because air resistance would slow you down. Everybody with me on that one? Now, what does this say in terms of conservation of energy? What does this say about direction? Does direction matter if I'm calculating how much mechanical energy an object has? It doesn't. Remember that energy is scalar. Okay, this sometimes fools people. If I'm talking about an example, like I said here before, of someone jumping out of an airplane. If you jump out of an airplane, which way are you moving initially? Horizontally, right? Newton's first law said, I mean, if there was no air resistance, you just jumped out of a plane, you would go right beside the plane. Okay, you'd start falling, but for that first second, you'd be at the same speed as the plane. In fact, all the way down, you would have that same horizontal speed as the plane, just like a projectile. Okay, remember that in this case, that's all the question is concerned about is what is your speed? Okay, it doesn't matter that it isn't vertical. You have speed, therefore you have kinetic energy. All right, so keep that in mind. Okay, a horizontal velocity still contributes to your mechanical energy if you are falling. Okay. All right, I want you guys to try this one. Okay, we looked at this video a while back, the Evel Knievel jumping over the canyon. All right, now we're going to treat it like a law of conservation of energy question, and we're going to figure out how fast he was going when he landed on the other side. All right, so the situation we have is that he is driving off of one side 70 meters above the bottom of the canyon, moving at 38 meters per second. When he hits the other side, he's 35 meters above the bottom of the canyon. We want to figure out how fast is he going when he hits the ground over there. All right, and remember that you want to start this off as a law of conservation of energy question. Okay, the initial mechanical energy is equal to the final mechanical energy. Okay, you don't have the mass. Okay, pick one. Pick any mass you like. Okay, I did this to a class I had once because I told them like 10 times, guys, if I don't give you mass doesn't matter, you don't need one. Okay, and I told them that like 10 times. Then during the exam, I had a person come up to my desk, Mr. Coderre, I don't think you put the mass on for question 4. I was like, oh, okay. And it was like a roller coaster. I said, it's like 5 kilograms. And they're like, what? 5 kilograms, sit down. And they sat down. And the next person came up and like, Mr. Coderre, I think you forgot the mass. I'm like, oh, it's 10,000 kilograms. And there's a few people in the class who realized that he's messing with them because mass doesn't matter. And they were chuckling. And these other people were like, oh my God, I'm so screwed. He gave that person 5 kilograms. He told that person 10,000 kilograms. They're still going to get both of them wrong. It doesn't matter. What happens to mass? It cancels. It's in every single term. Okay, you're multiplying every single term in this question by the same number. Therefore, that number can be whatever you want it to be. Okay, in fact, it's easier to just eliminate it in a law of conservation of energy question. Here's why. All right, so what we have, okay, is that we're trying to figure out the final velocity. So we're going to start out with EI equals EF, okay, and then we're going to say that that's EPI plus EKI equals EPF plus EKF, and then we're going to expand that out even further. M times G times H initial plus 1/2 MV initial squared equals M times G times H final plus 1/2 MV final squared. Mass is in every term. If I multiply every term by that number doesn't make any difference to the question. Okay. Remember, the other reason that is true in this question is that all things accelerate at 9.81 meters per second, regardless of their mass. That means that any object of any mass would be moving at the same speed at that same point where the motorcycle hits the ground. Okay, if I threw a basketball, motorcycle, I threw a motorcycle, okay, it wouldn't matter. It would be going the same speed at that point. Does everyone follow me there? Again, in the perfect physical world. Obviously, in the real world, it's different. Okay, so I've canceled mass. Now I'm left with this: GHI plus 1/2 VI squared equals GHF plus 1/2 VF squared. I'm looking for VF. So the first thing I want to do is move GHF over to this side by doing what? Subtracting it. So essentially I'm saying the mechanical energy, that's this side, minus the potential energy gives me the kinetic energy. That's what I'm saying, and that would fit because mechanical energy is potential plus kinetic. All right, I'm trying to get VI by itself, so now I'm going to divide both sides by 1/2, and then I'm going to square root. Now I've got VI, right? Very similar to what we did in some of those work energy theorem questions. All right, so now when I plug in my numbers, I have 9.81 times 70 meters, the initial height, plus 1/2 times 38, the initial velocity, squared, minus 9.81 times 35 meters. That was the final height, divided by 1/2. Yep. Whoops. You knew what I meant. Yeah, okay. So we got 9.81 times 70, okay, plus 0.5 times 38 squared minus 9.81 times 35, okay, divided by 1/2, square rooted. Okay, so we got 46.2 meters per second, right? Which is pretty fast. Okay, that's the speed that they hit the ground at on the other side. Okay, the only real trick to these guys is entering them into your calculator correctly. Okay, I have a lot of people who try to enter this whole thing in like one step with all brackets and trying to get the square root and everything. I find that even myself, I make a typo in there somewhere. Okay, so I go through it one piece at a time, and that way if I screw up, I don't have to go over the whole thing again. Okay, so just kind of keep an eye on that when you're entering. You got a lot of numbers to enter here, so make sure you're entering them carefully. All right, everybody okay with that example? Yeah. All right, so this is just what we just did and the explanations for what we did, so we'll just skip over that. All right, I want you guys to try this one. It's even easier than what we just did. We have a frictionless roller coaster car that has a mass of 800 kilograms. At one point in its journey, the car has a speed of 4 meters per second and is 35 meters above the ground. Later, its speed is measured to be 20 meters per second. So the first part wants you to calculate its total initial mechanical energy relative to ground level. And then the second part wants to know the gravitational potential energy when it's moving at 20 meters per second. All right, so you don't have to do as much algebra for this one as we had to do to calculate the final speed. All right, so I'll give you a couple minutes on that one. So we have this imaginary frictionless roller coaster. Okay, we know that its initial point is up here. Okay, we know the mass is 800 kilograms. We'll actually need that to calculate the energy because mass is part of energy. I don't need mass if I'm looking for height or speed because it cancels out. But if I'm looking for energy, mass is part of energy. I have to find that. Okay, or I have to use that. Sorry. So we know it has a speed of 4 meters per second here, and it's 35 meters above the lowest point. Okay, a little while later, its speed is measured to be 20 meters per second. I'm going to assume that's not at ground level. It's possible that it would be, but it's not likely. All right, so I'm going to assume that it isn't, especially since they were asking me what's the gravitational potential energy at that point. It would imply it does have some. All right, so the first thing I'm supposed to do is find the initial mechanical energy. Do I need to have this word in there? This is a conservation of mechanical energy question. Isn't that value the same everywhere? Yeah. Okay. They say initial because they want to give you a hint to use the initial data to find it, but it's actually the same everywhere. They could have just said find the mechanical energy of the roller coaster. It's the same everywhere on the track. All right. So we're going to find mechanical energy by taking potential and adding it to kinetic, and in this case we're using the initial values in order to do that because that's where we have enough information to do so. So we'll have 800 kilograms times 9.81 times 35 meters plus 1/2 times 800 times 4 squared. That was the initial speed of the roller coaster. All right, so 800 times 9.81 times 35 plus 0.5 times 800 times 4 squared. All right, so we have 281,080 joules worth of mechanical energy at any point along this track, okay? In particular, the initial point, but anywhere along the track, that's what the mechanical energy value will be. Now, they want me to calculate what's the potential energy here. Well, I'm going to go right back to this formula, except now I'm going to say, all right, the mechanical energy is EP final plus EK final, and I'm trying to solve for this. So what do I do with EK final? Subtract it over. All right, so I'll have then my 281,080 joules minus 1/2 times 800 times 20 squared. That will give me my final potential energy. Okay, so we'll take that number, we'll subtract from it 0.5 times 800 times 20 squared. whoop, not 2 squared, 20 squared. All right, so we have 121,080 joules of potential energy. I would say I wouldn't have asked for that. I would have asked you for how high above the ground it is. What additional calculation do I need to do now? Okay, what did I just calculate here? I calculated the final potential energy. Right? Well, that final potential energy is calculated by going m times g times h final, right? Right? Well, I know what the mass is. I know what gravity is. I take my 181,080 joules, okay, and I divide it by 800 times 9.81. Okay, I divide by mg, and that should give me the height there at the end. Right? So we're still 15.4 meters off the ground at that point. Oh, sorry, not 181. It's supposed to be 121. Sorry. I just wrote it wrong. I used the right number in my calculator, but I wrote this wrong. It should be 121,000. Sorry. Good eye. 121,080. Yeah. Okay. Questions on how that one works? Okay. Are these ringing a bell from Science 10? Somewhat. All right. So these are some examples of different types of law of conservation of energy questions. So for right now, I want you to just try 1 and 2. Don't worry about the human cannonball one yet. We'll get to that because that's actually going to bring a little bit of projectile motion stuff back in, okay, to the fray, which isn't hard. It's just one more thing to think about. All right, so try the one here with the crate and the one with the mass. It's a super creative question. Something like I would make up. Okay, so try 1 and 2, okay, and see how you do with those. Okay, remember, if you're looking for an energy type, so if it says look for the kinetic energy, you must include mass. If it asks you to find a speed or a height, mass will cancel. Okay. Just think about it from a units perspective. If they ask me to find energy, that's kilogram meters squared per second squared. Energy is part of that. Okay, or I'm sorry, mass is part of that. But if I'm just asked to find height, that's just in meters. I don't need mass for that. So for question number 1, okay, in an isolated system, that means ignore friction, okay, a crate with an initial kinetic energy of 250 joules and a gravitational potential energy of 960 joules is sliding down a frictionless ramp. If the crate loses 650 joules of gravitational potential energy, what will be its final mechanical energy? Well, where does that potential energy go? It becomes kinetic. So all I have to do is take this 650 joules and add it to the initial kinetic energy. Remember, they turn into each other as the object falls or slides or whatever. Okay, we're ignoring friction here, so all of it is conserved. All I do is take the 650, add it to the 250, and I should have 900 joules, okay, of potential, or sorry, of kinetic energy final. Okay. For number 2, we have a mass of 55 kilograms, 225 meters above the ground, moving at 36 meters per second. Okay? Use conservation to calculate its velocity when it reaches a height of 115 meters above the ground. Okay? Ignore the effects of air resistance. How many people are done number 2? Okay, so let's have a look at that. Okay, so we know then that the initial mechanical is equal to the final mechanical because they told us to ignore air resistance, which is the only force that would take energy away. So that's going to mean then that we're going to have m times g times h initial plus 1/2 mv initial squared equals mg h final plus 1/2 mv final squared. Right? We are looking for, okay, its velocity final. Right? That's what we're looking for there. So now we're going to solve for VF. What can I do with all the m's? I can cross them off. Now, on a test after that day where, you know, I messed with people, I kind of felt guilty. So now I just put a mass on there no matter what. All right? If you want to use the mass, you can. If you don't want to use the mass and recognize you don't need it, don't use it. Okay, it's entirely up to you. It will make no difference whatsoever if you use it or don't in a question like this one. All right, so I'm going to cancel mass because I like having less numbers. Okay, I'm going to solve for VF by first subtracting the potential energy over. So I'll have GHI plus 1/2 VI squared minus GHF, and that's going to equal 1/2 VF squared. So I'm going to divide both sides by 1/2, and then I'm going to square root. Okay, that'll leave me with VF. So it's the same calculation we did to calculate the speed of the motorcycle. Okay. Yes. So we got 9.81 times 225 meters. That's what they told us was the height. Plus 1/2 times 36 squared minus 9.81 times 115 meters, the final height. Okay, divide all that by 1/2, and we should get the speed of the mass, okay, at that 115 meter mark. So 9.81 times 225 plus 0.5 times 36 squared minus 9.81 times 115. Okay, divide that by 1/2, square root. All right, so this thing will be moving at 58.8 meters per second at that 115 meter mark. All right, everybody okay with that one? All right. This one with the human cannonball is a little bit more involved. Not a lot, but a little bit. Okay, a human cannonball in the circus is shot at 21 meters per second at an angle of 20 degrees above the horizontal. Okay, from a platform that is 15 meters above the ground. If the acrobat has a mass of 56 kilograms, what is his gravitational potential energy relative to the ground when he is at the highest point in his flight? Now, when he's at the highest point in his flight, he isn't moving vertically anymore, right? Because at the highest point, that's where you stop and start coming back down. But he is still moving horizontally. Can we calculate that number using what we remember from projectile motion? Okay, initially we know he was fired at an angle, right? We can find the horizontal component. That's going to be one of the things you'll need to do because you'll need that velocity if you're going to calculate his potential energy at the top. Okay. And then for part B, if the net in which he lands is 2 meters above the ground, how fast is he traveling when he hits it? Okay, that's strictly a conservation of energy question. Find a spot where you can calculate his mechanical energy. You know it's the same everywhere, including when he hits the net. Okay, you can use that to find his speed. All right, I'll give you guys a little bit of time on that one. Okay, see if you can figure that one out. Okay. I would say you have enough information to calculate the mechanical energy with just the initial information. When he's shot out of the cannon, there's enough information there to calculate his mechanical energy. Okay, so the first thing I want to do is calculate the mechanical energy of the human cannonball anywhere during his flight. I can do that with the initial information that they give me. All right, so I'm going to calculate the mechanical energy just because that's something I can do right now. M times G times H initial plus 1/2 MV initial squared. Okay, so I'm going to take his, what was his mass here? 56 kilograms. 56 times 9.81 times 15 meters. That's how high the cannon is, okay, right here, right, when he's fired. And then I'm going to add that to his kinetic energy, which is 1/2 times 56 times the speed he was fired at, 21 meters per second. And that's squared. All right, so that will give me the mechanical energy at any point in his flight. So 56 times 9.81 times 15, right, plus 0.5 times 56 times 21 squared. All right, so that's his total mechanical energy, 20,588.4 joules. Okay, that's how much mechanical energy he has at any point during his flight. Now, the second part is calculate his potential energy at the highest point in his flight. So here's what I have to remember about projectiles. Okay, if I fire him at a 21 degree angle, I think is what they said, right? No, 20 degree angle. Okay, so we fire him at a 20 degree angle at 21 meters per second. He is moving somewhat horizontally and somewhat vertically. I don't need to know this V initial, okay, it doesn't matter to me, But why do I need to know the horizontal? Because when he's at his maximum height, that's how fast he's going. Remember, he's no longer moving vertically at that point. The only velocity he has at his highest point is his horizontal component, because he will, for an instant, only be moving horizontally. He will not be moving vertically at that point. So that's why I need to know his V horizontal here. All right, if I know it here, then I can use it to calculate the kinetic energy that he has at his highest point. Then I can subtract that from this number, and I'll have his potential energy at his highest point. All right. I can also then at that point calculate how high he is at his highest point if I wanted to. All right. So the first thing I'm going to do is calculate VH because I need that. All right. So that's going to be the cos of 20 degrees times 21. All right, so his horizontal velocity is 19.733 whatever, okay, meters per second. That's how fast he's going here. All right, so now I'm going to calculate his kinetic energy at this point. So that'll be 1/2 mv squared. So that'll be 1/2 times 56 times that 19 point whatever it was there, 19.7 something, right? And that's got to be squared. So that's really important for me to keep all of my decimals on this one. So 0.5 times 56 times my answer squared. All right, so there's his kinetic energy at his highest point. All I have to do now is subtract that from the kinetic energy, or sorry, the mechanical energy that I calculated earlier, okay, which is that number there. All right, so I'm going to take the 20,588.4 joules, and I'm going to subtract the kinetic energy that I just calculated. All right, so I have 9,684.84 joules of potential energy at the highest point. Can I calculate how high he is now? All right, so this number here, the 9,684. Okay, that equals, his EP doesn't equal his EK, equals his EP. All right, so now I can say EP equals M times G times H, divide both sides by mg, and I'll be able to solve for H. So I'm just going to take that number that I just calculated and divide it by 56 times 9.81. Okay, he doesn't end up a whole lot higher than he was launched from. Okay, 2.5 meters roughly, okay, higher than he was launched from. But he was only launched at a 20-degree angle. It's not like it was really steep. Okay. Everybody follow me on how that works? I would not ask you one like that, okay? Not on a unit exam. I would think about it on a final exam because it combines 2 units into one question, but I don't think I'd be quite that cruel. Okay, pendulums. Pendulums are another example of something that obeys the laws of conservation of energy if, if we're in an isolated system. This is what happens when you cut money from education. Okay, you get ghetto physics. Okay, this is a drawstring out of my old hoodie and a roll of electrician's tape we found in the back. Okay, so yeah, you don't get a real pendulum when you cut money from education. So remember that. If you're old enough to vote for the guy who says more money for education, then you won't get ghetto physics. Okay. All right. So in a pendulum, okay, its normal position is what we call its equilibrium position. That's here. Okay, where it would sit if it had no energy at all. Okay. To give it energy, I have to do work. So I lift it away from its equilibrium position. When I let it go, okay, then it's going to swing back to its equilibrium position. But it's going to go right past it and go to the other side. Same height on both sides? Should be. And if we're in an isolated system, it should be the same height on both sides. Okay. Obviously, I'm helping this thing along a little bit. Okay. If I wasn't helping it, it would do this. Okay. You can see how it really quickly dies. okay, because it's losing a lot of energy to air resistance friction here at the pivot point. Okay, all I do is each time it goes through, I just give it a little nudge, okay, in one direction or the other to make it look like it's not losing any. Okay, but it should go to the same height every single time. Right, this is what Newton actually showed with, you guys have probably all seen like it's got the 4 balls or the 5 balls, and you pick the one up and you let it go, and they click back and forth, back and forth. Okay, that's Newton's cradle. He almost got beheaded for that. Well, he lived in a different time, but people thought he was a witch. Okay, because when he built that thing, and the one ball would hit one side, and then the other ball would magically fly up on the other side, people were like, "You're a witch." Okay, and we do all kinds of bad things to witches. We burn them at the stake, or we drown them, or we cut their heads off, or whatever. Okay, it was a very different time. So he had to really explain to everybody why that thing worked. Okay, and he was explaining that when he lifted the ball away, he wasn't magically doing anything to it, because that's what they thought, right? Well, he was a warlock, because male witches are warlocks. But anyway, he would lift that thing away from that side, and they thought, well, he's doing something magically to it, and that's why the one on the other side flies up. He said, no, I lifted it. I did, I gave it this living force. That's what they called energy in his time. Okay, that it can transfer to the other balls in Newton's cradle. Okay, and all it's doing is it's giving that living force back and forth, back and forth. The living force thing is the thing that nearly got him beheaded, because they're like, living force, magic, you're a witch. Yeah, okay, set you on fire kind of thing. Okay, that's what they were thinking. He had to explain as much physics as he could to the people in charge so he could not die over that. Seems silly now, but okay, that was essentially what happened. So a pendulum really just converts, okay, potential energy back into kinetic, back and forth, back and forth. Its mechanical energy is always the same anywhere in its flight, even if you turn into a chicken while I hypnotize you with my roll of electrician's tape. Okay, so with this ideal pendulum here, okay, it's suspended by a string. The string is 2 meters long. It's pulled sideways and released. The highest point of its swing is 25 centimeters, which we don't want to leave in centimeters. Okay, we want it to be in meters, 0.25 meters. Okay, above the floor. Okay, the lowest point of the swing is 5 centimeters above the floor. The mass of the pendulum bob is 250 grams. That's, by the way, what the weight on the bottom of a pendulum is called. It's called the bob. I don't know why, but that's what it's called. Okay, so we're looking for the mechanical energy of the pendulum relative to the floor when the bob is at its highest point. Well, that's not going to be too hard. At its highest point, it only has what kind of energy? Potential, right? This is where it stops before turning around to come back towards equilibrium. So all we have to do is go m times g times h, 0.250 times 9.81 times the height, which was 0.25 meters. Okay, so the potential energy there is 0.613 joules. Right, so not a lot, but it's not a very big mass either. It's quite small. Okay, then it says, what's the mechanical energy of the pendulum relative to the floor when the bob is at its lowest point? I ask this question all the time, and you wouldn't believe how often I trick people with it. Do you have to do any more math? No. Conservation of mechanical energy says that its mechanical energy is the same at all points on its path. Therefore, the answer is still 0.613 joules. All right, but if I put that in a multiple choice question, I would get a third of you on it. Okay, because it just says you automatically assume, oh, I got to calculate something else. Okay, not necessarily. Okay, that's testing whether you truly understand the law of conservation of energy. Okay, for part C, it asks, what's the kinetic energy of the bob when it's at its lowest point? There, I'm going to have to do a conservation of energy question. Okay, I'll have to do this. Mechanical energy equals EP plus EK. I already know the mechanical energy is 0.613 joules because I already calculated that. All right, I would just subtract the potential energy over and solve for EK. Right? I could also solve for how fast it's going at its lowest point if I wanted to at that point too. Okay, and then what's the speed of the pendulum? That's part D. Okay, we could solve for that. So let's just quickly solve those two parts there. Okay, if we have, we're going to bring EP over, so we're going to have 0.613 minus mass, which was 0.250 times 9.81 times 0.005 0.05, not 0.005, 0.05 meters. Okay, that'll equal our kinetic energy. All right, so there's our kinetic energy, 0.4905 joules, okay, which is less obviously than our potential energy, or sorry, our mechanical energy was. And then if I divide that by 1/2 times the mass, and then square root it, okay, it'll be moving at just under 2 meters per second at its lowest point. Okay, so still the same idea. Okay, all this question is trying to illustrate to you is you know how to do roller coaster questions, therefore you know how to do any law of conservation of energy question, whether it's a human cannonball, whether it's a pendulum, they're all the same. Okay, they all operate on this EI equals EF principle. Okay. Questions on that one? All right, so we're going to use the same. Actually, we're going to skip number 1 because we've already done that. Okay, we'll do number 2 here, which is a model rocket question. There's quite a few things to calculate with that one. Okay, those are the answers there if you want to check and see if you've done it right. Okay, so we got a model rocket, 3 kilogram model rocket. Okay, it's fired so that when it is 220 meters above the ground, it is traveling vertically upward at 165 meters per second. At that point, its fuel runs out. Okay, so there's no more work being done on it when its fuel runs out. It is now a law of conservation of energy question at that point. Okay, during the launching phase, obviously, work is being done. There's thrust there. Okay, more energy is being put into it. All right, so it resumes the rest of the flight without power. Assume there's no air resistance, okay, and that all potential energies are measured from the ground. All right, so we want to calculate the mechanical energy of the rocket when it's there, 220 meters above the ground. Okay, we want to calculate at its highest point what its gravitational potential energy will be, and how far above the ground it will be at that point, and when it hits the ground, how fast it will be going. All right, so you guys can handle that, and I'll give you a few minutes to get those. All right, let's have a look at number 2 here. So I know the mass of the rocket, it's 3 kilograms. I know how high above the ground it is when it runs out of fuel. I know how fast it's going when it runs out of fuel. Therefore, I can find its total mechanical energy at that point and every other point after that, including when it hits the ground, including at its highest point, okay, all of that kind of stuff. So the first thing I'm going to do is find the mechanical energy of the rocket by adding its potential energy initial to its kinetic energy initial, okay, and that'll give me the mechanical energy everywhere. So m times g times h initial plus 1/2 mv initial squared. So that'll be 3 kilograms times 9.81 times 220 meters plus 1/2 times 3 kilograms times 165 squared. Okay, so at that point and at every point thereafter, it has 47,312.1 joules. It's 0.1 joules, right? 0.1 joules. All right, so that's my mechanical energy at any point. That's part A. Okay, part B asks when it reaches its highest point, what will its gravitational potential energy be? All right, how fast is it going at that point? 0. It was fired vertically. It has no kinetic energy at its highest point. Therefore, the potential energy at its highest point is 47,312.1 joules. I don't need to do any more calculating if I recognize those simple things. Okay. C, how far above the ground is the rocket at its highest point? All right, well, now I've got to use this formula. I know the potential energy is 47,312. M times G times H. So I'm just going to go 47,300 and, whoops, did that wrong, 47,000. Okay, divided by 3 times 9.81 will give me the height, the maximum height. Hey, gentlemen, need you listening, please. All right, so the maximum height's going to be 1,607 meters. Okay, actually, I think we only have 3 significant figures there, so it'll be 1.61 times 10 to the 3 meters for the maximum height of the rocket. Okay, then the other part of this question asks, when it hits the ground, how fast is it going? Okay, when it hits the ground, how much kinetic energy does it have? All kinetic. 47,312.1 joules is its kinetic energy when it hits the ground. So to find out how fast it's going will be the square root of EK over 1/2 of m square rooted. All right, so I take my, so I go square root of 47,312.1 and divide that by 3 times 9.81. It'll be moving at 40 meters per second when it strikes the ground. Okay, everybody with me there? Wording of that question makes it seem like it should be a lot more difficult. All it's asking is, indirectly, do you remember a couple of things about projectiles? Okay, when they're at their maximum height, they have no vertical velocity. When they hit the ground, all their energy is kinetic, things like that. No, I'm at mass. Oh, yeah, I've multiplied by 9.81. Sorry. I don't know what I was thinking there. 47,312.1. Yeah, you're right. Divided by 1/2 of m, so 1.5. Sorry, I multiplied by 9.81, which makes no sense. Okay, yeah, there we go, 178. Sorry, 178 meters per second. All right. Now, I want you guys to try question number 4. Okay, I'll blow it up here so it's a bit bigger. Okay, give that one a try. Simple conservation of energy question.